This video, I'm going to talk about several different things. We're not going to go into a whole lot of detail. I'm just going to introduce several different topics that go along with correlation and scatter plots and least squares, regression line, line of best fit, and some other things. So I'm going to skip around a little bit. We'll deal with some of these notes that I'm putting on this video, and I'll send this set of notes to you, but we're not going to deal with the whole PowerPoint. We will come back to some of the PowerPoint in later sections. So just the first, again, I'm going to be skipping around a lot, so you just have to try to follow along, get what you can get. We're not going to start off with stuff that's really all that real difficult. Correlation is a relationship between two variables. So normally it'd be your x and your y. With your x and your y, that we still use the same setup that you use for any other graph. So x comes first, y comes second. X is your independent or explanatory variable, and y is considered your dependent, because y depends on what x is. You remember when you had equations in algebra, you had y equals 5x plus 2 or something like that, and you might have made a table of values. You had your x and you had your y, and you picked your x. Maybe you picked your x to be 2. Then you just stuck in 2 right there. So x could be anything, and then y depended on what you stuck in there for x, and y would have come out to be 12. Then your ordered pair was 2, 12. So it's the same idea. You got an x variable, you got a y variable. Your x is your independent. That's what's changing each time. They're both actually changing, but that's what's changing. And your y is your dependent. It depends on what the x is, and it's also called the response variable. So what's the response from what x was? A scatter plot can be used to determine whether a linear correlation exists between two variables. All that means is, if we're looking at some graph, we want to know as the x gets bigger or smaller, so as whatever we have on this axis goes out farther, what happens to the y value? Does it come up, if it's just a random scatter plot and it just looks like this, then it really doesn't look like what the x is affects what happens with the y. But if we have another scatter plot and it looks more like this, then it looks like as the x gets bigger, the y also gets bigger. And that's what correlation is. Is there that correlation? As the x gets bigger, does the y get bigger? As the x gets bigger, does the y get smaller? So on, so on, so on. And we're dealing with trying to have a straight line correlation here. Is there some line that goes through there? And probably, if you remember back to geometry, I told you never ever to say straight line, because all lines are straight. But here they actually use that term. So is there some correlation that exists between the two? As one moves, does the other move in the same, in a correlating direction, or in a direction that's the same for all the different points? An example, if we have this table of values here and we graph them, we started with x was 1 and we had -4, then x was 2 and had -2, x was 3, -1, x is 4, 0, and X was 5, 2. Well, as we're looking at that, it looks like as the X goes up, so as X goes up, the Y also goes up. So if we were going to make a prediction off of that, if we were going to pick X is 6, we would probably guess that the Y is going to be something larger than 2. It's also going to go up. That's correlation. As X increases, Y tends to decrease in this one. This is called a negative correlation. So as the X, here you see X is right here, X is probably small, maybe 1 or something. The Y is pretty high, so Y is maybe like 7. But as we go over, as the X's get bigger, the Y's get smaller. So anytime you have a graph that looks like this, negative correlation. So that has a negative correlation. That's one of the key ideas that we're going to cover today. One of the basic things is whether you have a negative correlation or whether you have a positive correlation. Positive correlation, as the X's get bigger, looks like the Y's also get bigger. So that's a positive correlation. When you have something that looks like this and it's just sort of all scattered everywhere, then we can say that there's no correlation. No correlation. And then sometimes you'll have something that looks like this, and we won't deal a whole lot with this right now, except to talk about what this graph looks like. And this is a nonlinear correlation. It doesn't just represent a line, it looks like it represents a parabola. So it's a nonlinear correlation. And you could have other graphs that are nonlinear correlation. So you got a negative correlation, a positive correlation, no correlation. Then you could also have a nonlinear correlation. All right, here I'm jumping to the notes just because I want to touch on a couple of things on the notes that I sent to you, or that were attached with everything. Again, it goes over scatter plots. Independent variable is X, dependent variable is Y, and then there's some other stuff here with line of best fit, or least squares regression line, so on and so on. We're going to talk about that here in a little while. How the regression line runs, correlation coefficient, that's R. We're going to talk just real briefly about it today. We'll talk about it more later on in other sections. Here's where we're positive or negative, just shows how you're moving. If there's no correlation, then your R equals 0. And I just wanted to show these graphs here. So if you have a correlation where R equals 1, you have a correlation where R equals 1, like this, like the first graph here, that's called a perfect positive correlation. So if your correlation coefficient, again, we're going to talk about it, the correlation coefficient more later, but for now I'm just introducing these different kinds. If you have correlation coefficient R that's 1, then you have a perfect positive correlation. If it's a -1, like in the second graph, then you have a perfect negative correlation. And then if you have where R is like 0.8, and we're going to talk about this more, and we'll have set rules for this. If your correlation coefficient is 0.8, -0.8, then you have a high correlation. When you find R, if it's like in this next graph, the one on the bottom row here, when you have R equals 0, so your correlation is 0, that means that there is no correlation to the variables, to your X and your Y. And then the last graph, if you have a correlation of something like negative 0.3, then that's telling you that you have some correlation, but when it's 0.3, 0.2, stuff like that, as it gets closer to 0, that means there's not as much correlation. And again, we'll have rules for all that when we talk more about R, but I just want you to see that if you have R equals 1, then it's a perfect positive correlation. If R equals negative 1, then it's a perfect negative correlation. So sometimes we'll have if it's a perfect correlation, then that means it's going to be just a perfect line, and our line of fit is going to just be one exact line, and we can predict everything exactly. And that doesn't happen real often. And again, we're not going to learn today how to calculate R, but it is on those notes, and we'll use these notes again. And we can use our calculator to do some of this. We're going to come back and talk about some of this here in a few minutes. I'm going to go back to the other. All right, so this is an example of just making a scatter plot. An economist wants to determine whether there is a linear relationship between a country's gross domestic product, the GDP, and carbon dioxide emissions. The data are shown in the table. Display the data in the scatter plot and determine whether there appears to be a positive or negative linear correlation or no linear correlation. So we have all these numbers. Your GDP is how much your country produces. So that's our X here. That's how much each country produces. And then the CO2 emissions, that's how much carbon dioxide that the country puts out. That's your Y's. We're trying to decide whether, as the gross domestic product goes up or down, what happens to the amount of carbon dioxide that that country produces. So we have all those, and we can graph them. We graph them and it looks like this. Remember your GDP, that's your independent variable. That's we're starting off knowing that this country was just over $1 trillion there, or right at 1 trillion or so. And we're trying to figure out, how does that affect how much CO2 emissions that they put out. And just looking at this, it looks like as the GDP goes up, it looks like that the amount of emissions also goes up. So it looks like it has a positive correlation. So that's one of the things that we're predicting. We're going to graph these and then decide whether it's got a positive or a negative correlation or no correlation. Next one, Old Faithful, located in Yellowstone National Park, is the world's most famous geyser. The duration of several of Old Faithful's eruptions and times until the next eruption are shown in the display table using TI 83 and 84, and we won't do this very much, graphing these on the TI 83, 84, because it takes a lot of changing of your settings on it, and it sort of messes stuff up, and you got to make sure it gets back. but we'll talk about it a little bit. So if we go, and what we would do, you enter in the X values in the list 1, Y values in list 2. Go to stat plot, and you got to set up your stat plot, and that's what messes up things when you start changing the stat plot. And then our graph looks like this. And from all that, it looks like that there's a positive. If we look here, it's going up as the X's get bigger, the Y's get bigger, so it's got a positive linear correlation. You can, I'll give you this. This is the way you do it on your calculator. If you want to do it, just remember that when you do this and you go to stat plot, when you change that stat plot, then it messes up all the other graphs, and you got to make sure you go back and reset it and put it back the right way. You may have to set your window to make sure that you can see all the Y's and X's. The correlation coefficient is also called the Pearson product moment coefficient, and that's the R. It has a lot of different names. We're not going to talk a whole lot about it today, and this is the formula, and we're going to come back to this. We're not going to deal with the R right now. We'll come back to it. But I will talk about the range. The range of the correlation coefficient always has to be between -1 and 1. So when you're dealing with your correlation coefficient, it's always going to be between -1 and 1. Again, -1, if it has an R that's a -1, that would be a perfect negative correlation. If it has a R that's 1, then that's going to be a perfect positive correlation. If it's close to 0, so if your R falls somewhere in here somewhere, and we'll talk more about that range, then there's very little or no correlation. If it's exactly 0, then there's no correlation. As you get closer and closer to 0, that means there's very little correlation between the two variables, that they're not really related to each other, they don't really affect each other. 1 is a positive, perfect positive correlation. Strong negative correlation, and again, we'll talk more about this. Strong positive correlation, weak positive, or weak or nonlinear correlation. We can have all these different things, and there's a range when we're looking at that between when we have 0, -1, 1. As you get closer to -1, you get a stronger and stronger negative correlation. As you get closer to +1, you get a stronger positive correlation. And if you're going the other way, as you get closer and closer to 0, you start off where, maybe here at 0.8, you have a fairly strong positive correlation, but as the correlation, or as the R goes down, as you get closer to 0, you have a weaker correlation. All right, the last thing I want to talk about is your line of best fit, or your least squares regression line. It's called a bunch of different names, and I'll call it different names every so often. But the line of best fit's the one that we'll probably use the most. And this is the formula for the line of best fit. Is y hat equals a plus bx, and a lot of times that y hat won't even be on there. That's just to sort of symbolize, I think, for the fact that it's a regression line. But in this formula, the number that's with or the coefficient that's with the x, that's always your slope. Then the other number is your y-intercept. Now sometimes those two get switched around, so sometimes it'll say instead of y equals a plus bx, sometimes it'll have a as the slope, so it might say something like b plus ax, or it could switch the two around, it could say ax plus b, so on and so on, but the number that's with your x is always your slope. Then the other is your y-intercept. So whichever way it's written, it's always that way. And again, this is your line of best fit, and sometimes we'll just call it the line of fit from now, because we're not going to go into how to find the line of best fit right at the moment. All right, I will tell you a little bit about it, but we're not going to go into how to find the exact line that's the line of best fit until another class. All right, so I picked up this graph. I have no idea what this graph is, just one I picked up off the internet. It says your independent variable is number of people. Your dependent variable is the time on a tightrope. So we got our x and our y, and then they gave us a few points here as a scatter plot that they have. Let's go back here. Sorry, it's messing up on me. So they gave us a few points here that we have just as a scatter plot, not very many, and it's probably going to be more than that normally. And what we want to talk about is the line, the regression line, or the line of best fit. Now, if we just draw a line up through here, and there's things that have to occur for it to be the line of best fit. And again, we're not going to go into detail this time on those things, all right? All I want you to do is make a prediction of the line of fit, or line of best fit. So if we draw something like that in, now what normally happens, or where you get this regression line from, is you have to figure out for each point how far it is from that line of best fit. And what happens is you take all of those distances and you find the average of them. So we take them all, and this time we take, there's 1, 2, 3, 4, 5, 6, 7 points. So we would find all those distances, add up all the distances, and then we would divide it by 7. And what we want there is we want the line that's going to go through here that gives us the lowest answer for that. All right, and again, I'm just going over this stuff to try to give you some idea of where this comes from. We're going to use our calculators to calculate that most of the time, or a computer or whatever. But that's where that line of best fit comes from, is it takes all these points and sees how far they are from each line, and it keeps going until it gets that line that has the lowest average of all the distances the points are from the line. And we're going to figure out how to do it out longhand also. But for this assignment, all I want you to do is estimate this line of fit. So we just want to give an estimate, all right? if I'm looking at this, I would probably just pick a couple of points. First thing, if we're gonna write an equation, y equals a plus bx, remember a is your y-intercept, the b is your slope in that form. If we're gonna write the equation in that form, we wanna find that a and that b and just write some easy equation for it. All right, the easiest thing, if I draw in this line, and it looks like something like that, it looks like the y-intercept, which is our a this time, is going to be somewhere maybe 7, 8, 9, 6, somewhere in that range. All right, yours could be a little different, but it's going to be somewhere close to that. It's not going to be 35. All right, plus then to find the slope, to get an estimate of the slope, we could just pick 2 points that maybe we sorted the coordinates of. This point right here looks like it's about, let's say 3, and then it goes up to 15. And then we have another point over here, let's use that one. And it has coordinates of, looks like it goes out about 9 and up 25. And then you're just going to use the slope formula that you had in algebra. M equals, you subtract the y's on top, so y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We're just making an estimate here again. I can't say that enough. So we find those slopes, or we find this slope. Our y's this time, remember your y's for slope, the y's are on top, that's always your second number. So I'm going to turn them around and I'm going to write it 25 minus 15. It doesn't make any difference which order they're in, as long as if I take this y first and this y second, then I got to do the same thing for the x's. So I went from this y to that one, that means I got to start with this x and go to that x. So on bottom I got 9 minus 3. 25 minus 15 is 10. 9 minus 3 is 6. Just divide that out. 6 will go into 10 once, so 1 point, with 4 left over, 1.6 repeating, or 1.67, something about like that. That's going to be our slope. So 1.67 times x. The line that we drew, that is pretty close to the equation of that line, and that's our line of fit. Again, it's not the line of best fit, but it's a line of fit. And all I want you to do for right now is just make a prediction on about where that's going to be. Now, some of the problems on the assignment that I'm giving you will be multiple choice, and maybe they have an answer that looks like this: y equals 6 plus 1.6x. Well, that's pretty close, and if it's multiple choice, that's probably your answer. You just want to go with the one that's the closest to what you came up with. All right? So, again, line of fit, just coming up with your y-intercept, where the line crosses the y-axis, where it crosses that axis right there, and then your slope, you can pick 2 points that are fairly close to the line, and just make an estimate of the slope. No matter which 2 points we pick, we should come up with a slope somewhere close to that. What we're going to do once we have that line of fit is we're going to make predictions off of it. So if I go back to this and I want to make a prediction about what happens when there's 12 people, 12 people might fall right in here. So I want to go back here. All I'm going to do to make that prediction is go up from where x is 12 and then go over here and make a prediction. And it looks like y then would be about 28 maybe. So you're just making a prediction off of that. And we could make it right off the graph. We could also pick x is 12, and once we wrote this line of fit, we could stick in 12 right here for X, do the math, and if I do that math, hopefully I didn't just screw up and say Y is about 28. It should be somewhere fairly close to that. So 1.67 times 12 plus 7. And I end up with about 27.04. So that's pretty close to 28. We're just making a prediction off that, probably just because my line going across through here is not drawn very well. My line going up here wasn't drawn very well either, probably. So we could make that prediction and say that if we just plug into this formula or use the graph, plug into the formula, and we could make a prediction what Y should come out at X being 12. When we do that, when we start making these predictions, if we're within the range of data that they gave us, so on this, if I go back to this, if we're within, it looks like we went out to, I don't know, somewhere about 18 maybe. So we went out to 18, we went from 0 to 18. So if we're within that range and we're making predictions off of the data that we actually have here, then that's called an interpolation. Not sure why that just drew a triangle. So that's called an interpolation. When you're inside the data that you were given, so if you're inside the data that you were given, pen's all messing up. So if you're inside, that's interpolation. If you're outside the data, so if I go back to this, if I wanted to predict out, if I wanted this to go on out and I wanted to predict out at 25, so that'd be outside there, then that's called extrapolation. So interpolation, you're predicting inside the data that you know or the data that you were given. Extrapolation, you're predicting outside the data. So if we wanted to predict, if we go back to this one, and we wanted to predict at 25, again, we could make our graph and come on out here somewhere and see where we would hit our line of fit, or we could just use this and stick 25 in for X and see what we come out with and estimate how much time on the tightrope that those 25 people spent, or whatever this graph is. So again, the main things here, that line of fit, know that you have a slope and a y-intercept. Know your positive correlation, negative correlation. We're not worried about the exact R value, your R coefficient yet. All we're worried about is being able to pick out positive correlation, negative correlation, and then making predictions with interpolation or extrapolation. If you're inside the data, it's interpolation. If you're outside the data, then it's extrapolation. The worksheet will be due Sunday. It's not a very difficult worksheet. Just try to do your best on it. And you can just send it to me, picture or whatever, email, however is easiest for you. Again, the test that you're supposed to send to me, make sure that you send it by email.